Dear students, welcome to this lecture on digital logic and system design. Today we are going to look into the design of a simple computer. But before we go on designing a simple computer, we need to learn what is the instruction format for such a computer, because any computer will operate on the instructions that it may follow and it may execute, right? So I'm taking three instruction code formats. This is called the operation code. This will be a binary number, which is a binary code corresponding to an operation. For example, if this is 8 bits, I'm just taking an example. If this is 8 bits, then 0000, all zeros will be one operation, 00000 1 will be another operation, and 00010 will be another operation, and so on, right? Finally, 11111, all ones will be the 256th operation in such a computer. A total of 256 different instructions may be possible. So this is the operation code. Over here things are implied. The very operation code will say that I have to move data from some register R into some register A, right? Then the other code format will be an operation code followed by an operand. It requires an operand to carry out the operation. This is said to be immediate operand, where the operand as a part of the instruction itself will have to be brought into register A. And finally, operation code followed by the address of operand. So the operand over here is not a part of the instruction, but it is the address of that operand is a part of the instruction. So the data or the operand has to be fetched from the address given over here in the memory, and it has to be brought to register A. So this is called direct addressing. So this is implied. No operand is given explicitly. It is implicitly meant to be one of the internal registers where the data has to be taken from and has to be loaded into register A. But over here, the operand is a part of the instruction itself, and over here the address of the operand is a part of the instruction, right? So this is called implied addressing, this is called immediate addressing, this is called direct addressing. By addressing I mean the addressing of the operand. This is implied operand, immediate operand, and direct addressing of the operand that needs to be brought, right? So this will become more clear when we see more slides. Let me give you an example of instruction code format. Opcode is equal to 1, which means this may be loaded somewhere in the memory. The program or the instructions have to be loaded into the memory. So suppose this is the address 25. So at address 25, opcode 1 is stored, which simply means move data from some register R to register A, right? But when the operand, the operation code, or in short called opcode, is 2, that means the operand has to be the next memory location, right? So this is operand into A. If opcode corresponding to this is at 35, then the operand has to come from 36, and whatever is stored here at location 36, that will form the operand. So basically 44 has to be moved into register A. This data 44 has to be moved into register A. Now the third kind, where opcode is 3, direct addressing. This is the opcode. This opcode will tell me that I'm talking about direct addressing. So the very next instruction, which is a part of the very next byte, which is a part of the instruction, will give me the address. Right? And this address will give me the operand. So I'll go to this address, and from here I'll pick out the operand. So this 28 will come into A, and not 70. 70 will not come into A. Over here 44 came into A, right? But over here 28 will come into A because my opcode is different. If this is the opcode 1, then implicit addressing, R has to go into A. When opcode is 2, then immediate addressing, that means the operand is the very next byte. And when direct addressing opcode, which is 1 is there, then the next byte or the instruction byte will give me the address, and from that address I have to pick out the operand, or I have to seek the operand and load it into register A. So this is how the difference between these three lies, right? So now is the time that we understand what is the difference between a macro operation and the micro operation. A micro operations usually runs in one clock cycle. This is a statement that may take a sequence of micro operations for its implementation is called a macro operation. So a macro operation may have more than one clock cycles to complete itself, whereas a micro operation usually gets completed in one clock cycle. So this is in essence the difference between a micro operation and a macro operation. For example, operand into A. This statement is a macro operation because it specifies a computer instruction. To execute the instruction, the control unit must issue control functions for the following sequence of micro operations. In order to affect this macro operation, I have to carry out these many micro operations. In the first micro operation, I'll have to read the operation code from address 35, as we saw here. This one. This will be a this will be a macro. This is a micro operation, all right, but this is a macro operation also. This is a macro operation. I am taking the example of this one, right? Read the operation code from address 35, transfer the operation code to a control register. The control decodes the operation code and recognizes it as an immediate operand at instruction, so it reads the operand from address 36. And finally, the operand read from memory is transferred into register A. So it will take 4 micro operations to complete, or even more. We will see shortly precisely how many micro operations will be required to affect this. But in essence, the difference between a micro operation and the micro operation we should understand very clearly. Micro operation usually gets done in one clock cycle. A macro operation takes a series of micro operations and hence a series of clock cycles in order to affect itself. Usually, a computer instruction is a macro operation. Usually, uh, right? In fact, this will also be a macro operation because this is a computer instruction. It is just that it will take one clock cycle to complete itself. So a macro operation may take one or more clock cycle, whereas micro operation will usually take one clock cycle. Now, suppose we have the building blocks of a simple computer. What all we are having? We are having a memory unit, a small memory unit for that matter, 256 into 8, which means 256 locations of 8 bits each. What does it mean? It means that it will have the address line 8-bit wide. So for this memory unit, both address line as well as the data line will be 8. Why? Because into 8 means data is 8-bit wide and 256 is essentially 2 to the power 8 into 256, right? So 8 address lines and 8 data lines. This is memory address register. This is memory buffer register that we already know of. This will supply the address to this memory, and this will either take data out of the memory or will supply data into the memory, right? Now, there are also two special purpose registers. This is the instruction register which will hold the opcode, right? So whatever be the opcode that is fetched from here, that will come into this instruction register. And this will supply, this is program counter. This will supply the address of the opcode. So in a sense, just as MAR and MBR are generic for are the generic memory address register, and MBR memory buffer register for any kind of data, they are specific. PC and IR are specific for instructions. This is program counter is essentially the memory address register for an opcode. An instruction register is a memory buffer register for an opcode. Okay, we will see, things will get clear more. So they are special purpose registers, just as MAR and MBR are special purpose registers. Now the whatever the opcode is fetched into the instruction register, that will be decoded, and depending on the decoding, one of these control lines will go high. If for example it contains 00001, then Q1 will be high. If it contains 00010, then Q2 will be high, and 00011, then Q3 will be high, and so on, right? So this is the operation decoder. Now this operation decoder output are the control signals coupled with the timing signals, right? These two together will carry out several control signals for affecting the data move between memory unit and register A and register R. These are two, I can say they are general purpose registers or scratch pad registers with the name A and R. They may have any data, right? So this is the block, this is a timer counter. So it will receive the clock pulses, and suppose since I'm having T0 to T7, this shows that this timer should be 3 bit wide, right? 3 to 8 timing decoder will be 3 to 8. So it will count from 0, that will be T0, then 1, that will be T1, T2, T3, T4, T5, T6, T7, and after T7 it will get reset because this is the 3-bit counter. So that is why I'm having 8 timing signals T0 to T7. So this is the building block of a simple computer. Next, this is basically the list of registers for a single computer. Memory address register will be which will be 8-bit wide. I told you the reason. 256 into 8, so 256 is 2 to the power 8, 8-bit address line. That is why memory address register is 8-bit wide. Holds address for memory. Memory buffer register is also 8-bit wide. Why? Because this is into 8, so memory unit is 8-bit wide. So this will be 8-bit wide. It holds contents of memory word. Then A is a special is a general purpose register or a scratch pad register. It is called processor register, and similarly R is also another processor register. Both of them are 8-bit wide. They have to be 8-bit wide because the data is 8-bit, so every processing will be carried out in 8 bits only. Then program counter is also 8-bit wide because it holds address of instruction, and 8-bit why? Because the instruction will also be loaded in the same memory. So if this memory is 256, which is 2 to the power 8, so both PC and MAR both holding addresses. This is holding address of data, this is holding address of instruction. Both of them will be 8-bit wide. Likewise, IR has to be 8-bit wide because the instruction or the opcode which is coming out of it will be 8-bit wide because the contents of it are 8-bit wide. So that in that sense, MBR and IR both will have to be 8-bit wide. And finally, this timer counter. This is a register, a counter register, a register which can count, which is 3-bit wide. I just now told you why 3-bit, because this is a 3 to 8 decoder generating 8 different timing signals. So this is basically a sequence generator. What has to be done after what? This is what this timer counter will decide, or the timing counter will decide. Now, since this is a very simple computer, we are just designing it for 3 basic instructions. One of them is move R, which we know is implicit addressing, R to A, as we have seen. Move the contents of register R to A. Mnemonic means, you see, opcode is in binary, but it is very difficult for us, the human beings, to understand or to decipher or to remember the opcode in binary. For us, letters are more convenient. So this is for our understanding sake. The computer doesn't have to do with this mnemonic anything. It is for us. This mnemonic is meant for us. So operation code, what is the description? This will move R to A. This will load operand into A, where operand is a part of the instruction itself, and load operand specified by address into A. So this is LDI OPRD, load immediate. You see, mnemonic is such that we can see from the mnemonic itself what does it do. This says load immediate OPRD, right? OPRD into A. Load direct register A. Load direct register A, and address is specified. So the contents of the location specified by address in the memory, they are loaded into A. So these are the 3 basic instructions that we are trying to design this simple computer for. Now let us see what each of these instructions, they are macro operations. They are macro operations. So what is the series of micro operations that each of them will require? First thing will be instruction fetch cycle, which will be common to all 3. The instruction has to be fetched first. The opcode has to be fetched first. So this could be called opcode fetch cycle or instruction fetch cycle. Macro operation statement for this is the memory contents specified by the address stored in the program counter will have to come into IR. And this will be the macro operation, and program counter has to be incremented so that it points to the next location now, right? Remember, yeah, this one. Once, program counter will have to store this 25, 35, 36, whatever it will store. Suppose it stores 25, then this will come out into instruction register. If program counter stores 35, then this will come out into the instruction register. If it contains 45, then this opcode will come out into the instruction register. In these two cases, after we have fetched it, it should get incremented. Program counter should get incremented so that it points to the operand or it points to the address in the next clock cycle, right? So that is why we see program counter incremented. So this will be the macro operation which will be done by these three micro operations. First of all, PC goes into the MAR. Whatever be the contents of program counter, that will go into the memory address register, because memory may be accessed only by the address specified in MAR. So transfer the opcode address into MAR, then bring the MAR. In fact, when we are not mentioning the address, that means address is implicitly coming from MAR. So this may be written as MMAR into MBR, right? And PC gets incremented. And finally, whatever we have got into MBR will come into IR. So you see, we started with the PC, brought it into MAR, then MMAR into MBR, and MBR into IR. Three basic micro operations will be required in order to do the instruction fetch cycle, and this instruction fetch cycle will be common to all the instructions of a computer, because every time the opcode fetch have to be done before anything else can be done, right? So it will eat up three clock cycles, T0, T1, T2, right? Now next, let us see, after this common instruction fetch cycle to all of them, move R. What should be the micro operation corresponding to move R? In fact, after the opcode fetch has been done and instruction register has been decoded, right? Remember, this was the block. Yeah. Instruction register has been decoded. Now this will raise any one of these signals. So if it is the IR contains 0000001, then Q1 will be raised high and all of them will be 0. So that is why what I'm doing is corresponding to this, I'm saying Q1 T3. Q1 because the opcode is 00001, and T3 why? Because till T2 the opcode fetch has been happening, right? So the next one should be T3. So Q1 and T3 should do R to A, and timer should be reset so that the next time it starts from T0, that is opcode fetch or instruction fetch itself. So this will be the micro operation corresponding to move R, provided that the instruction fetch has already been done. Now take the next instruction, LDI OPRD. Over here the control signal raised is Q2 because the opcode that has been fetched by the common opcode or instruction fetch cycle is 0000010. So 10 raises Q2, right? Raises Q2. And T3, why? Because till T2 opcode fetch was being done, right? And after IR gets decoded, I get to know that Q2 is raised high. So now Q2 T3, what all we have to do? PC needs to be loaded into MAR. Why? Because this PC is pointing to operand now. You see, opcode fetch itself, it was incremented. So now it is pointing to, or PC contains the address of the operand. So I need to fetch the operand. So PC gets loaded into MAR, then MMAR is brought into MBR. So effectively, my operand has reached MBR and PC gets incremented. PC gets incremented. Why? Because the contents of the PC have been loaded into MR, so it should point to the next instruction now, right? And finally Q2 T5. See, this is a sequence: Q2 T3, Q2 T4, Q2 T5. Whatever is there in MBR, in fact that was the operand, right, which is fetched from the memory, that gets loaded into A, right? So and timer gets reset because the address the instruction has come to an end. So this will be LDI OPRD, right? Now the last one, LD address, the third instruction, PC gets loaded into MAR. Why? Because it is loading the address into MAR, and whatever is there at that location that comes into MBR. So what has come into MBR? The address of the operand has come into MBR now. You know, this PC is pointing to the next, is pointing to ADRS. Over here it was pointing to OPRD. So OPRD was directly brought into MBR and into A. But over here it is pointing to address. So this time the address gets loaded into MBR, and whatever is fetched from there goes into MBR, and PC gets incremented. Now this MBR goes back to MAR. Why back to MAR? Because now MAR is added with the address of the memory, and this M into MBR will bring me the operand now, will fetch me the operand now, and this operand will finally get loaded into A, and timer will be reset. Once again, note that PC need not be incremented here. Everywhere when we were doing MMBR, we were incrementing the PC, but over here PC need not be incremented because the address has already been fetched. You see, go back here and see. Yep. Opcode address, right? So after fetching the opcode, it gets incremented, it points here. After fetching this address, it gets incremented and point to the next instruction in the sequence, and that's it. It should stay there, right? So that is how these are the series of micro operations, and the control signals will be Q3 T3. Why Q3? Because when we'll bring in the opcode of LDA address, which is 00000011, that will raise Q3 as high, and T3. Why? Because till T2 it had been in the instruction fetch cycle common to all three of them. So Q3 T3, PCMAR, Q3 T4, Q3 T5, Q3 T6, and Q3 T7, and timer gets reset. Over here, even if you don't reset the timer, it will automatically, when incremented, will get to T0 anyway, because it was capable of holding only 7 clock cycles, generating 7 clock cycles, which all have been exhausted only in this particular case, LD address, right? So this is the execution of these instructions. Next, what we have to do, so we summarize here. We summarize by saying that fetch cycle requires 3 clock cycles, PC to MAR, M to MBR, PC incremented, MBR to IR. So the opcode is available in IR now. For move, I have to do one more clock cycle in addition to these 3 of the opcode fetch with Q1T3, because if this IR is 000001, then Q1 will be high. And what it does, it simply transfers the contents of register R into A. Register R is an internal register to the computer. It need not be having any address because it is a register. Register doesn't have an address, memory has the address, and timer resets. LDI will have 3 of them, Q2 T3, Q2 T4, Q2 T5. Q2 T3, what does it do? It loads PC into MAR. The PC which was incremented and pointing to the operand, that operand gets loaded into MAR. The address of the operand gets loaded into MAR, and that content from that memory location goes into MBR, and MBR comes into A. Along with it, I increment the pointer program counter here, and I reset the timer. Right? LDA, that will take 5 more clock cycles. PC goes into MAR. It loads the address of the address into MAR. Now this address is brought into MBR, and this address is loaded back into MAR, and the contents of the address, which is the operand, now will come into MBR, and MBR will finally be brought to A, and timer will be reset. So this is how these things can be summarized. Now I have to take all these register transfers and see what all are the control signals corresponding to them, right? For example, PC to MAR. Where all is it? PC to MAR is T0 or Q2 T3. You see, T0 or Q2 T3. or Q3 T3. So any one of these three PC to MAR should be done. I am just giving it a new name X1, right? Then let me see what is next. MBR to MAR. See, MBR to MAR. MBR to MAR. There is only Q3 T5. There is only Q3 T5, and I am naming it as X2. Then PC incrementation. Where all is it happening? Over here. So T1 or Q2 T4 or Q3 T4, right? T1 T1 or Q2 T4, Q2 T4 or Q3 T4 or Q3 T4. That's it. So that takes care of incrementing the PC, and I'm naming it as X3, right? Then M to MBR, which effectively means MAR into MBR. That memory location whose address comes from MAR, I want loaded into MBR. So let us see where all it exists. In fact, it exists at all these locations of X3 plus Q3 T6. I can see, sorry, yeah, it exists here, it exists here, it exists here, and in addition, it exists here, right? So incrementation of PC where all it was happening plus Q3 T6 or Q3 T6, right? So X3 or Q3 T6 it happens. Now MBR to A. Let us see MBR to A where all it happens. MBR to A happens in Q2 T5 and Q3 T7. So Q2 T5 or Q3 T7. Any one of these is going to affect the MBR into A. And R to A. Moving R to A is happening at only Q1 T3. So I'm writing Q1 T3 and naming it as X6, giving it a new name, a new variable X6. And then timer reset. It happens at three places, right? What are these three places? Q1 T3 timer reset. It happens at X5 plus X6, it says. So X5 plus X6. Let us see. Q1 T3. It happens at Q1 T3. It happens at Q2 T5. It happens at Q2 T5, right? And then it happens at Q3 T7. It happens at Q3 T7. So X5 5 plus X6 if I take, that will be X7 corresponding the control signal corresponding to T timer reset. And finally MBR to IR. MBR to IR is happening at only one place, T2, right? So I'm naming it as T2. So these are the control signals. X1 equal to this will do PC to MAR, X2 will do this, X3 will increment program counter, X4 will move the memory into memory location specified by the address MAR into MBR, X5 will move MBR into A, X6 will do R to A, X7 will reset the timer to 0, and X8 will move the contents of MBR into the instruction register. So this will be the design of the simple computer. All this combinational circuit will go inside. All this will go inside. What are the inputs? The inputs are Q1, Q2, T3 of the combinational circuit and the timers, right? So timers T0, T6, T7 coming from here from the timing decoder, right? And other inputs are x1 x2 so on, all these x1 x2 x3 x4 x5 x6 x7 x8, all these, and these are the outputs generated by the combinational circuit. T0 and T1 T2 T3 T4 T5 T6 will be the inputs, and Q1 Q2 Q3 will be the inputs, right? And where are Q3 Q2 Q1 coming from? The decoder at the output of IR, right? So it accepts these inputs, and generates these outputs. Now let us see X1. X1, what does it do? X1 moves PC to MAR. See, X1 is selecting this multiplexer, and when this is high, the multiplexer goes into MAR. So PC goes into MAR. See, PC goes into MAR, X1 does this. Now X2, see, X2 is here. X2 is here. What does it do? X2 has to load MAR with MBR, right? So MAR with MBR. right? MAR, this is the load signal with MBR, right? See, this is the second multiplexer. When X2 is high, that means X1 will be 0, and X1 is controlling the select line for this multiplexer. So when X2 is high, X1 will be low. So I will have MBR directed to the output, and that gets loaded into MAR, provided the load signal is high, and the load signal is being controlled by X2, right? So this is done. Now PC incremented. So X3 should simply come and increment the PC. This is what X3 does. Now X4 is loading the memory with MBR. Sorry, it is loading MBR with the contents of the memory. So X4, what all it does? See, X4, right? It controls the read signal of memory. It controls the read signal of memory, and it controls the load of MBR. So whatever comes out of memory, that will be loaded into MBR, right? That is what it does. M into MBR, right? M into MBR, and the address will come from MAR, which must have been loaded in the previous clock cycle, right? So this is taken care of. Now MBR to A, simple. What is it? X5. MBR to A is X5. So let us see X5. X5 is driving this multiplexer. So it takes data from where? From MBR. You see, it takes data from MBR and bringing it into A, supplying the load signal and setting this multiplexer up in such a way that MBR is directed, the contents of MBR are directed. So MBR gets loaded into A. See how do I traverse this? MBR is loaded into A, right, by this control signal. That is what was to happen. MBR has to be loaded with A. Now X6 R to A. So X6 is, when X6 is high, X5 must be low, so R should be directed by this multiplexer at its output. So either when X5 or X6 is, either one of them is high, A has to get loaded. In one case, A has to be loaded with MBR. In the other case, A has to be loaded with R, right? In the case of X6, it has to be loaded with R. A has to be loaded with R. And when X5 is high, it has to be loaded with MBR, right? Sorry. Yeah. A has to be loaded with either MBR or R, depending on whether X5 is high or X6 is high, right? And finally, X7, see, X7 clears the counter or resets it to 0. And if X7 is not there, it has to increment. This is active low counting. That is why I'm seeing an inverter here. So whenever anything other than X7 is there, it keeps incrementing it, so that from T0 there is a transition to T1, there is a transition to T2, T3, T4, and whenever X7 goes high, regardless of where this timer has reached, it will reset it to 0. So that is why X7 is taken as clear and X7 bar is taken to increment, right? Okay. So that is about X7, and finally MBR to IR, which is T2. So MBR to IR, MBR to IR. So X8 simply supplies the load terminal of IR, and this IR is always receiving data from this MBR. So this will be loaded into IR, right? You might think that it is receiving from two places. No, it is not receiving, because this is the data going out of MBR into memory. It's not coming out of the memory. So it is from MBR always. So this is design of a simple computer. You still have to realize this combinational circuit using this logic. And then this circuit is capable of running three basic instructions. This is capable of running these three basic instructions. right? So see, this was the block. Now we have provided all the connectivity to it in the final slide. Provided all the connectivity to these blocks. Memory 256 into 8 MBR, which is 8 bit, R which is 8 bit, A which is 8 bit, PC which is 8 bit, MAR is 8 bit, IR is 8 bit. This is a 8 to 264 decoder, but I'm just making use of three of these lines, because there are three instructions, three opcodes only. This is a 3-bit counter, and this is a 3 to 8 decoder, giving me the signals T0, T6, T7, right? So this is how I can design a simple computer. This may be your first computer that you have designed today, a basic one of course, but you have designed it nevertheless. We'll stop here. Thank you very much. Try to go through it. It has been an intense lecture today, but try to understand it. Any clarifications, you may contact me for it to be clarified. Thank you very much.